In this video, we will consider the double angle formulas for sine, cosine, and tangent. That is, we discuss and illustrate formulas for sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Importantly, we cannot simply factor the 2 out from the function input. We will state and prove each formula, and then consider specific problems in which the formulas are used. First, we have sine of 2 theta is 2 times sine theta times cosine theta. Next, we have that cosine 2 theta equals cosine squared theta minus sine squared theta. Shortly, we will have alternate versions of this identity. Finally, we have that tangent of 2 theta is the ratio of 2 tangent theta over 1 minus tangent squared theta. The proofs of these formulas result from straightforward application of the addition formulas. First, sine of 2 theta equals sine of theta plus theta, which equals sine of the first, cosine of the second, plus cosine of the first, sine of the second from the addition formula, which equals 2 sine theta cosine theta when we collect like terms. Now, cosine of 2 theta can be written as cosine of theta plus theta, and using the addition formulas, we get cosine of the first, cosine of the second, minus sine of the first, sine of the second, which can be written as cosine squared theta minus sine squared theta. Finally, we have that tangent of 2 theta is tangent of theta plus theta, and using the addition formula for tangent, that's the sum of the two tangents over 1 minus the product of the two tangents. And so that simplifies to 2 tangent theta over 1 minus tangent squared theta. Now that we have the formulas, let's consider an example. Given that sine of theta is 4/5 and theta is in quadrant 2, find the values of cosine theta, cosine of 2 theta, and sine of 2 theta. We have 3 quantities we need to find. By the Pythagorean identity, we know that cosine squared theta equals 1 minus sine squared theta. So substituting in 4/5, we get 1 minus 4/5 squared, or 9/25. Therefore, cosine theta equals plus or minus 3/5. But since theta is in quadrant 2, we know that cosine theta is negative, so cosine theta is negative 3/5. Now we can look at cosine of 2 theta. The formula gives us cosine squared theta minus sine squared theta, and we can plug in our values. We get negative 3/5 squared minus 4/5 squared, which simplifies to negative 7/25. Finally, sine of 2 theta is 2 sine theta cosine theta, so we have 2 times 4/5 times negative 3/5, or a negative 24/25. Notice that since cosine of 2 theta and sine of 2 theta are both negative, we know that 2 theta is a quadrant 4 angle. Let's consider a second example. If x equals 4 sine theta, with theta between 0 and pi over 2, express sine of 2 theta in terms of x. This problem could simply say find sine of 2 theta, but we are given a hint that the expression will involve the quantity x. Since sine of 2 theta is 2 times sine theta times cosine theta, we know that we're going to need to find both sine theta and cosine theta. Both of these values will be positive since theta is in quadrant 1. We can solve x equal 4 sine theta for sine theta equal x over 4. Now we can use the Pythagorean identity and substitute x over 4 for sine theta. We want to solve for cosine theta, so we subtract x squared over 16 from both sides and combine the fractions. We take the square root of both sides, but we know that cosine theta will be positive, so cosine theta equals the principal square root of the quantity 16 minus x squared over 4. Now we're ready to find sine of 2 theta by evaluating 2 sine theta cosine theta. We substitute our expressions involving x for both sine theta and cosine theta. Finally, we simplify to get that sine 2 theta is the quantity x times the radical 16 minus x squared over 8. As I mentioned earlier, there are alternate forms for the identity of cosine of 2 theta that are useful. The formula we already know is cosine 2 theta equal cosine squared theta minus sine squared theta. One alternate form is cosine of 2 theta is 2 cosine squared theta minus 1, and the other form is that cosine of 2 theta equals 1 minus 2 sine squared theta. The proofs of these identities require clever use of the Pythagorean identity. First, we start with cosine 2 theta equals cosine squared theta minus sine squared theta. Then we substitute 1 minus cosine squared theta for sine squared theta. Finally, we distribute the negative sign and collect like terms to get 2 cosine squared theta minus 1 as desired. For the other version, we again start with cosine 2 theta equal cosine squared theta minus sine squared theta, and this time we substitute 1 minus sine squared theta for cosine squared theta. Finally, we collect like terms to end with 1 minus sine squared theta. For our final example, let's consider a problem in which one of the alternate forms of cosine 2 theta is useful. Let's verify the identity cosine 3 theta equals 4 cosine cubed theta minus 3 cosine theta. Usually, when verifying identities, we like to start with the more complicated expression and simplify it in hopes of arriving at the other expression. This time it isn't clear what simplification of 4 cosine cubed theta minus 3 cosine theta would be helpful, because we don't know any identities for cosine of 3 theta. Since we do know the addition formulas for cosine, we can start with cosine of 3 theta equals cosine of 2 theta plus theta, and then use the addition formula for cosine to expand cosine 2 theta plus theta as cosine of the first times cosine of the second minus sine of the first times sine of the second. Next, we can make double angle substitutions for both cosine 2 theta and sine of 2 theta. Since our goal is to have an expression in powers of cosine theta, we choose the version of cosine 2 theta equal 2 cosine squared theta minus 1. When we multiply the two factors of sine in the second term, we get a factor of sine squared theta, which we can also write in terms of cosine squared theta. So we make that substitution using the Pythagorean identity and distribute the factor of cosine theta in the first term. There's more distribution to do in the second term. So we distribute the minus 2 and the cosine theta, being careful with the SIG ends. Finally, we collect like terms to get 4 cosine cubed theta minus 3 cosine theta as desired. Verification of new identities using known identities takes a lot of practice with frequent misstarts and algebraic pitfalls. Unfortunately, there's no magic path to proficiency other than practice to gain the insight needed to make useful substitutions. Do not get frustrated when your first or second attempts go awry. This is how you gain experience.